do have a lot of questions from the audience, and we'd be honored if you could take some of them up.
Sure.
So, the first question I have is that I assume most of these uh, control tests are done under inert conditions. So, what are the odds that the use of such condensers allows a reaction to occur at room temperature and ambient conditions that would otherwise not be possible?
Oh, that's a great question. So part of this I talk about a lot about rate acceleration. So if I back up, I don't know if I can find this quickly, but if I back up, I keep showing rates that exceed the Sabatier maximum. So a lot of times people are saying, oh, you're making faster catalysts. So you think about what a faster catalyst is a catalyst that achieves the same rate at a lower temperature. And so a lot of these applications here, our interest is not necessarily in making a faster catalyst because we might hit some of their limitation like diffusion, or we might have not good thermal control at rates that high, but I could lower the overall temperature or change the pressure of my reaction to be able to do that. And so what you're asking about, could you take reactions and drive them down closer to room temperature? That's a possibility. How close can you get to room temperature depends on the chemistry, where you start from, and how much you can accelerate the rate. But I think a lot of times people think I'm only talking about accelerating reactions. Really, I'm changing the conditions you could use that catalyst at. That's a great question.
Thank you, Professor. My next question has to do with the ion gel based condenser. The question is whether the ion gel moves under the impact of the electric field, and does the electric field create a diffuse layer with gradient of concentration inside the gel, and how does that actually impact the actual operation of the device and of course the catalytic reaction itself?
So I'll start by saying the ion gel has been around for a long time as for incorporation in capacitors. And there's a lot of these answers are out there in the literature already. I'll say that. But in short, I'm not the expert on this, but the ions do move. So you think of the pairing of these charges at the surface, like you can think of this reconstruction happening close to the surface to pair a positive charge I apply with a negative charge in the ion gel. So there is some mobility of these ions in that particular material. Hope that answered the question.
Yes, thank you, Professor. The next question has to do with if we replaced, let's say, the alumina with something like a magnetic material, something that contains cobalt or nickel, there seems to be some literature out there that suggests magnetism also affects catalysis. So in this particular case, the application of an electric field would obviously also change the electromagnetic properties. So do you expect that there could be some interesting outcomes from that?
So I've heard of these materials that where application of a magnetic field changes the catalysis. I have limited knowledge of those materials, so I can't really speak intelligently about what the effect would be. I think the question was, though, if I put a magnetic sensitive material into this condenser, would it be affected by this electric field, which might induce a magnetic field change? I don't know the answer to that immediately, but anytime you're changing charge like this, you're inducing at least short-term magnetic field changes. So I guess it's possible, is what I would say.
Thank you, Professor. My next question has to do with slide number 31 of your presentation. Uh, So being from an electronics background, this actually resembles something that we used to call a band pass filter.
Yes.
So what we do with it is only allow certain frequencies to go through the device and filter out what we don't need, the noise, so to speak. This got me thinking, does changing the frequency in terms of this graph also affect the selectivity and not just the, rate or the efficiency?
Those are both great questions. So I would say two things. We just wrote a preprint, which is currently in peer review, where we model these systems as bandpass filters, and they're very effective for that. So the answer to that is yes. Several years ago, we wrote a paper on a concept toy reaction. We have A react to B and A react to C. I don't have a slide on it here, unfortunately. And the question was, could we use dynamics to control the selectivity? And what was very exciting to me about that was you could actually take catalysts that were very poor at selecting for either B or C product and change the selectivity dramatically, almost perfectly to either product, depending on the conditions you pick. Now, this is something we want to look at in the future is if you have complete control over surface dynamics, can you use this to control selectivity for reactions that have been very difficult to control in the past with a static material? There's a whole world of selectivity control we have not been able to explore yet, just because we're building up to that. But I think in terms of economic impact, there's a huge opportunity here to use programmable catalysts to improve selectivity.
Thank you, Professor. Uh, the next question has to do with these condenser devices. They effectively constitute what seems to be like an interfacial heterojunction device. So, in terms of the band structure at the interface, uh, optimal operation, do we look for a flat band or do we look for some kind of band bending in term if we were to draw the band structure at these interfaces, the one between uh, the alumina layer and the graphene and the hafnium
Yeah,
oxide and the
I think
silicon.
this is a great question. Let me find the picture here. So if I think of alumina graphene system is more complex because it's an insulator for a bulk alumina. For a thin film of amorphous alumina, it's have a lower band gap, but it still has a band gap. So I think the question becomes, I think another way to rephrase this is where does the charge accumulate in these surfaces? So if I think of removing charge from this particular system, the defect states on the surface, which are the active sites, will exist as in the band gap itself. So those defect sites are unique in that regard. So if I remove electrons, those are the first place I'm going to remove electrons from. Now, when I think about alternatively, you have a metal on graphene. This I can think of this more as a continuum. And the question is, where am I removing charge from that surface? Well, the graphene and the metal interaction, of course, always exists. So if I remove charge from graphene, it's also interacting with the metal. It's changing the metal itself. More complexity of that depends on so many factors. It's hard to answer very simply because the graphene can have different amounts of oxygen. The clusters can adhere to the graphene differently. They can be different sizes. They can have different facets. But generally, that's the thinking about how this works and how I think of the electronic state of that surface. There's so much more to be done to understand it, though.
Thank you, Professor. So, in terms of from a physics perspective, the way we see it is there's charge generation, charge annihilation, and recombination effects. And what I want to ask here is whether you have actually looked into recombination rates based on the frequencies applied.
I haven't. So beyond the impedance spectroscopy I showed, I haven't looked any further just because I've kept our focus completely on catalysis and catalytic applications. I am very interested if people have ideas of studying these that I'm not aware of because I understand, think of the complexity here. These are electronic devices with catalytic chemistry and the mathematics of dynamics all put together. That's part of the benefit of our team approach is we're able to get that, but it's still, even still then, there are all sorts of new ideas people have out there for how we can study these. I'm open to suggestions and ideas for collaboration if people can think of new ways to study these that I'm not aware of.
Thank you, Professor. My next question and last one for now is whether you have observed any thin film thickness effects in these when you fabricate these devices. Is there something like an optimal thickness or is it too much, too little?
That's a great question. I didn't talk about this, but the answer is yes. So actually, I have it here in the data. So the data in red here is the plot you see on the right. So you can see this peak is shifting from left to right in terms of the CO binding energy. And you can see that reflected here. That is a very thin layer of these little nanoclusters of platinum that are about 2 to 3 nanometers thick. If I put down 10 nanometers, a complete film of platinum, you're completely shielding this effect and you kill it. So you can see that no matter what voltage I apply, the device is dead. So quite simply, I can put more electrons into a surface, but I can also put fewer places for the electrons to go by decreasing the loading. So the most extreme version of this is to put single atoms down or extremely small clusters of metal such that more charge goes into fewer sites. So yeah, we did this as kind of a check on the device. Can we understand what's happening? And the answer is that's exactly what you expect. It shields the charge from the top layer.
Thank you, Professor. So with that, the Q&A is concluded. I'd like to hand it over to Neha.
Thank you so much, Kaushik, for moderating the Q&A. And thank you so much, Professor Paul, for such an insightful Q&A session. So from all of us from ACS, we would request you to put forward some concluding remarks for our attendees. Professor Paul, am I audible?
Yes.
So we would request you to please put forward some concluding remarks for all our attendees.
Well, I just want to say thank you to everybody for attending. It's a privilege to speak to so many of you, and thank you for ACS for putting this together. I think I've been working on this project for 5 years, and my excitement over what's possible with this just continues to grow. I think when we look at the simple simulations we do into the more complex simulations, all we see is an incredible increase in the power of controlling surfaces and controlling chemistry. It might take a while to get to the point where we can actually modulate and control surfaces the way we want, but you can see that the potential for controlling selectivity, rate, conversion exists fundamentally no matter what approach we take. I talked about catalytic condensers. We could use pulsed light. We could use dynamic strain. There's many different ways this could be done. And I would encourage people to, if they're interested in this, there's all sorts of opportunities to contribute and to use creative solutions to modulate surfaces with time. There's immense potential here, I think, moving forward.
Thank you so much, Professor Paul. This brings us to the end of today's session. We hope that you enjoyed this broadcast, and we invite you to view our edited recordings in the ACS Science Talks library. The attendees will receive your certificate of participation along with a survey form about your experience regarding the ACS Science Talks. On behalf of all of us at ACS, thank you for joining us today. We hope to see you again for future events. Till then, stay safe and healthy. Thank you so much for joining in, and thank you so much, Professor Paul, for this wonderful lecture. Thank you so much. Have a great day.
Thank you.